I guess it's 4. I'll get started. Good evening, everyone. I'm Apoorv, and today we are going to explore what I like to call the intersection of the chaos, securing AI infrastructure on Kubernetes. As the last speaker, I know I hold a very important responsibility, and that's to get you all out to the bar in the next 25 minutes. I promise I'll do that. Quick background about me. I'm a security engineer at Microsoft with research interest in Kubernetes, containers, and application security. So here's the reality. Every company is now an AI company. If you're not already running LLMs in your Kubernetes, you will be soon. And look at this architecture. The user input comes in, goes through an API gateway, talks to an LLM inference pod, maybe talks to a vector DB, and here's the interesting part, tool execution. AI today have access to loads of tools, be it for code execution, web fetching, file access, anything that you'd want. And as a security engineer, that's where the real stuff is. So our roadmap, we'll cover why the threat model is different, look at the major attack patterns that I've seen in the wild, and then shift to practical defenses that you can implement. I'll leave you with actionable items for the Monday morning. So this is the key insight, the threat model shift. In traditional app security, you control the validation layer. User input goes through your code before it does anything. But with AI apps, the LLM is in the middle. And you don't really control what is being passed to the tools, what's being passed to the kernel. It's unpredictable by design. Prompt injection means user input can effectively become code. And you are basically just talking in English for it to execute code. So moving on to our first attack pattern, and that's sandbox escapes. Ever asked your favorite LLM to analyze a CSV because you are too lazy to do it? Try following its thinking traces, and you will see LLM pulls up a code exec interface. That's the sandbox. The promise, it's an isolation. However, the reality might be different. We have seen sandboxes running as root because they needed to install pip packages, or maybe because the pod died and they had to restart it in privilege mode. Internal services accessible on localhost, no egress filtering whatsoever, and the cloud metadata service wide open. This pattern is shockingly common. It looks simple, but we have seen it. The sandbox is actually giving you a false sense of security. So here's what the attack actually looks like in practice. An attacker crafts a prompt that gets the LLM to run this exact code. We aren't looking for a complex buffer overflow here. We are just using the tools that we built. In here, we see the attacker can exfiltrate HC password or any environment variable directly to their C2 server. Even worse, they can hit IMDS service at 169.254 IP. That is there to harvest the cloud credentials. If that works, they don't just have your container, they also have your cloud account. And there's no exploit needed, really. You just needed to ask it nicely. From a Kubernetes perspective, this is where the gap becomes a chasm. On the left, you see what the security team thinks that you deployed. The textbook secure pod manifest, it's non-root, the file system is locked down, egress is denied, it's perfect on paper. But look on the right side. Because many AI frameworks and sandboxes need to perform tasks like pip install at runtime, or if you attended CAT talk yesterday, pods die, and you have to restart the pods. And oftentimes, during debugging, you will start that in a privilege mode. That's a risk. When this happens, the pod itself might often default back to the root access mode. Developers might also skip network policy because they are facing some issues while debugging. The result is that your secure sandbox is actually running with full root privileges, unrestricted network access, and a direct line to your cloud metadata server. The one thing that I want you to take from this slide is audit what's actually running, not just what you intended to run. And you will be golden for a lot of attacks that we are talking about. Moving on to the next major pattern. It's our favorite OWASP kit, SSRF. Attack pattern 2 being SSRF through vision APIs. Describe the image at this URL. Sounds innocent, right? But what happens? The URL gets fetched server-side from the cloud provider's infrastructure, and what if the URL points to IMDS IP? This is SSRF as a service. You are literally asking the AI provider to make server-side requests for you, and many of them will happily do. Now, I'll be honest, there are block lists, and you might not be able to reach it directly, but try doing a redirect, a 307 or 302 redirect. There's the talk tower problem, time of check versus time of use. They validate the URL at request time, but the actual fetch happens much later. In between, the URL does a 307 redirect to an internal IP, maybe IMDS IP, and legitsite.com is actually loaded with IMDS credentials. That's because the fetcher is flowing the redirect through a different code path than what's actually doing the validation. Takeaway here is revalidate after every redirect, and that will also protect you from a lot of these redirect type of SSRF attacks. Now, on to the third major pattern, and this one's big, cross-tenant isolation failures. Consumer AI platforms are multi-user by nature. Your code is running next to someone else's code on shared infrastructure. And here's what breaks. Predictable IDs, internal APIs that trust anything, session state that doesn't know whose session it is. The moment you can list someone else's session and execute in their context, that's the whole ballgame. In Kubernetes terms, network policy works great for pod-to-pod isolation. A can't directly talk to tenant B, but what about shared services? The database, the cache, the internal APIs, even the internal bootstrapping code that's used for your code sandbox. They trust the traffic because it's internal, but there's no tenant context which is flowing through, which means the service layer is actually the weakest layer. You need identity-aware access, not just network positions. Okay, let's shift to the defenses. 5 principles for zero trust with AI workloads. 1, never trust LLM output. 2, sandbox doesn't mean secure. If it just says sandbox, add real isolation. 3, egress filtering is mandatory, not optional. 4, block IMDS, period. And 5, tenant context must flow through or be provided to the internal APIs. These aren't just theoretical, they directly counter the attack that we have just discovered. Okay. Moving on, the first defense, network policy for egress. So the YAML that you see here, that blocks the metadata service by IP, blocks all RFC 1918 private ranges, and only allows HTTPS to the, that one. Yeah, the key here is the except block. Explicitly deny internal ranges. Don't rely on allow what you need. Also deny what you definitely don't need. This alone, I think, would have stopped so many of the attack patterns that we have seen with multiple providers. Pod security context. Run as root is non-negotiable. If you need package installation, use pre-built images with everything baked in. Read-only root file systems prevent persistence. Dropped capabilities reduce the attack surface. Seccomp profile runtime default blocks dangerous syscalls. These are table stakes. If your AI sandboxes don't have it, fix it soon. And finally, the standard containers versus the kata debate. Standard containers share the host kernel. That's a massive attack surface. One kernel exploit, and you're already on the host. Kata containers, or gvisor containers, take a different approach. They run your workloads in a lightweight VM with its guest kernel. There's real hardware-enforced VM boundary. Even if an attacker gets kernel-level access, they are in the guest kernel, not the host. They'd need a hypervisor escape, which is much, much difficult to target. Azure uses this for confidential containers. The performance and pricing overhead is slightly higher than traditional containers, but for code execution sandboxes, which are handling untrusted AI input or handling sensitive data, that trade-off is definitely worth it. If you're on Azure, look for confidential containers. If you're on-prem, Kata is open source and integrates well with Containerd. For SSRF defense, here's the pattern. Pass the URL, resolve DNS, check the IP, and then do your own validation. The key here is that while loop that we see. Every time you hit a redirect, you re-resolve DNS and recheck the IP. That defeats the talk tower bypass. Don't use allow redirects equal to true blindly, and you're golden. Handle redirects manually with validation at each hop. And talking about IMDS hardening, for AWS, require IMDS v2 tokens, maybe set hop limit to 1 that blocks containers from reaching it, since the token request won't actually go beyond 1 network hop. For GCP and Azure, use workload identity. Your pods authenticate with their own identity, not the node service account, and that eliminates the need for IMDS entirely. Workload identity is the right answer. IMDS is a legacy pattern that shouldn't exist in modern deployments, especially the AI deployments. Detection matters. These are the signals to definitely alert on: any egress to IMDS IP, DNS lookups to metadata URIs, outbound traffic to non-allow listed IPs, cross namespace traffic that shouldn't exist. If you're on Azure, Defender for Containers has a built-in alert for metadata server access. For deeper runtime detection though, I love Falco. It's open source, Kubernetes native, and you can write any custom rules for exactly these types of scenarios. Okay, so what do we do Monday morning? Immediately, audit your egress, what your AI pods can actually reach. Block IMDS with network policy and IMDS v2. Enable workload identity, and check if your sandbox are running as root. Add Falco rules, that's a cherry on the top. For longer term, evaluate gvisor or Kata for code execution workloads, and consider a service mesh for tenant isolation with MTLS. These are all actionable. Start with the audit, know your current state, and go from there. 4 things to remember. 1, AI workloads need new threat models. The LLM is untrusted. Tools extend your attack surface in ways traditional apps don't. 2, sandbox might not always work as intended. Ensure through audits that sandbox configuration is set to isolated. 3, SSRF via AI is already building upon traditional SSRF attack vectors. Vision APIs, web fetching, tool uses, all of these are SSRF vectors. Revalidate after each redirect. And 4, multi-tenancy is genuinely hard. Tenant context must flow through each layer, but shared services are where, from an attacker's perspective, all the golden eggs are. So protect that service layer. That's the talk. These patterns are based on active research. Specific findings are pending disclosure, but attack techniques are real and the defenses work. With that, we are open for questions.
How do you know you need the IMDS though?
Oh yes, that's why. I think tenant isolation is definitely hard, but at least we can add defense in depth layers, right? Like we can start with egress filtering. If we do need IMDS, maybe switching to a workload identity or federated identity provider instead of direct IMDS line. I think that's something. But we need to work in layers so that IMDS, the crown jewel, is protected somehow. Yeah.
Hi, first of all, thank you. I'm just really happy to see this talk.
Oh, yes.
And I'm Leo. I was giving the how to eat blue team CTF's talk yesterday, so we talked about this problem.
Yes.
And the URL one was actually really interesting to me because I agree that obviously we thought think about that attack. And I was kind of wondering if there's a more Kubernetes aligned way to like give, because basically people do like to speak to the internet and URLs they want, and so just telling them no is not very, they will be unhappy if we tell them no. Yeah. And so we're trying to figure out how to balance, giving them some flexibility, but also giving them controls to lock it down. Ideally, as web users with that in their own subtenant, they can get a bit of controls here. I was wondering if there's like a Kubernetes aligned or Kubernetes native way that you recommend thinking about that.
Honestly, very specific to Kubernetes, I am not aware. There might be. The way I would approach it is like what the internet access or what additional access is needed for, then maybe go like restricted approach. Okay, these IPs or these FQDNs are reachable. Maybe redirect everything through a proxy. I don't know. I don't know specific to Kubernetes. There might be, but like these would be the general ones probably. Oh yes. So I think. So a lot of issues that I've seen, and let me go back to that slide. Okay, it's not working. I'll just answer. I couldn't go to that slide. But what I mean by tenant context is, I'll just leave it. So a lot of scenarios that I've seen are not because the tenant context was flowing through the upper layer or the application layer that was shown to me. It was because of these shared services which were running. Maybe one was submitting jobs, or I don't know if you have used E2B. E2B is the new code execution interface that the AI providers are using. And as part of E2B, there's the shared service which is used to initialize a job, list the job, maybe access files from other mounts and everything. So that shared service doesn't have any concept of who the user is or what the context is. And since that is lost in the translation there, that IDOR attack becomes very much possible in that instance. And we go from there, like trying to exploit those shared services. Awesome. I think with that, we'll end the presentation. Thank you, folks. Yes.